Okay, then let's continue. Yeah, just opening the file, minerals and rocks. So, and then we are going to the last slide from last time. Continue. Yep, that was it. So now we are continuing today with this one. And this is now a small introduction into the igneous rocks. As you know by now, igneous rocks can be subdivided in volcanic rocks, these are extrusivas, and in plutonic rocks, then these are intrusivas. In the extrusivas, they are much more fine grained because they are cooling down very fast in contact with the air, or even much more faster when they are coming in contact with water. And then you have the plutonic rocks. These are then the intrusivas, and they cool down very slowly, and therefore you can observe the crystals, yeah? So next slide. So in these igneous rocks you have the different textures. You have the macro textures, and the macro textures, this is just the way how the rock looked like in the end space event, yeah, like this one. So you can observe this just in the field, and in the field, I mean normally you are using a hammer. So while we are talking about the field, we should arrange so that they can get the field books. Yes, that Zug and the order, yeah. So and then you should have a field book, yeah, waterproof book, that you can also read the things what you have written down 10 years later as well. So and then you have a hand lens. So with this hand lens you can then identify in the field the different minerals as far as you know them. So and then you can already write down after this course all the chemical formulas from these different minerals, yeah? So now to your question from last week, because last week he was a little bit annoyed by seeing all these mineral chemical formulas, and he was asking me for what this is useful. Then I can say you now it is very useful, because when you have the mineral chemistry of such a rock, yeah, I mean in reality you are making afterwards then a thin section out of it, then you can observe these minerals inside or under the microscope. And then you are going to an electron microscope, and then you can measure all the mineral chemistry inside. And then you can calculate under which pressure and temperature this rock was formed. So and that is actually a very important thing if you are looking into mining industry, yeah? Because when you know the rock forming minerals, then you know the regarding or the corresponding ore which is inside. So when all these ore minerals are formed in different geotectonic settings, with a different main rock mineralogy at a certain pressure and temperature. So and another thing, another very important aspect why we are doing this, that is when you know the pressure and the temperature when this rock was formed, then you can calculate the heat or the temperature in a certain depth. So of course you have then to do some additional calculations, because during time they are cooling them a little bit down, but here in Fiji that is working very well because the crust here is very thin and very young and has not cooled down, yeah. So and that is then, for example, very important to get an overview of regarding temperature in a certain depth, and that is then good for geothermal power, yeah? Because there you need the temperature in a certain depth that you can boiling up the water very fast, and then you can run a turbine, and that is one positive effect, yeah? Because that, therefore, you will not have longer power cuts here in the town or in some other South Pacific countries. So again, it's just an academic play for me, yeah? So anyway, you have seen this, you are subdividing them in, you have the macro textures and then the micro textures, and then you can do the research. Then you have to distinguish what rock type it is. Is it as an inchless rock? And if it is an inchless or magmatic rock, then the question to be answered is it an extrusive or an intrusive? And that you can do by now as well, just by looking at all these rocks here, yeah. Here we have a lot of inchless rocks, yeah. And that, for example, is an extrusive or cooled down very fast. There you cannot observe any minerals inside, it is just glass, yeah. So this is also an extrusiva, yeah, but has still some other minerals, and these are some antibones inside which it has picked up on the way when it came up to the Earth's surface. So whereas if you are looking at other boxes, is not here. Here they are, yeah, there you have the plutonic rocks, and these are the granites, and they are all very, very coarse-grained, yeah. You know this now because they cool down very fast, and then crystallization can take place, yeah. So in the crystallization process, you are just doing here now in the glass. So I mean, you can mineralization can take place just by fluids, yeah, and here we have a solution, and now from this solution we are making then a crystal. Or you can do it by a melt which is cooling down. So and therefore, I mean, some of the melt, granitic melt is not that hot, there's about 750 degrees Celsius, whereas a basaltic melt can have 1200 degrees Celsius, something like this, yeah. So and that is just too hot to reproduce it. For us, are using just the glass, yeah. Otherwise, we would do this. So then you have some other rocks. You have sedimentary rocks, yeah. And these sedimentary rocks you can subdivide in chemical sediments, in biogen sediments, and what else? In clastic sediments. So and where do we have here some sediments? I think here they are around. Well, these are metamorphic rocks. But here we have some sedimentary rocks, and you can see they are by far. That is a dolomite, yeah, dolomite, that is a chemical sediment, yeah. So, and then we have here, for example, what do we have here? We have another dolomite. So, and what do we have here? That is a travertine. So, that is then biogene, yeah. So, and you can feel it is very light, yeah. So, here we have, for example, some gypsum. So you can actually just coming here, and then you can watch them. So sedimentary rocks are actually, for me as a petrologist, not rocks, yeah. This is just single grains, and they become baked together. There's nothing to do much with sediments, at least for me. So, and then we have my most loved rocks. These are the metamorphic rocks. So, and they are orogenic. So that means they are subduction related or collision related. And then we have local, we have then contact metamorphic rocks, yeah? So, and here we have a metamorphic rock, which you can find here on Fiji Islands, yeah? These are garnet-bearing green schists, yeah? So, and this is a real green schist, and it is green because of the mineral chloride, which makes it green, yeah? So, and then we have the others, we have a lot of metamorphic rocks. Where if you put them, here we have two boxes of them. Yeah, here you have a very famous one, that is the eclogite. Yeah, we have a bunch of eclogites here, 5 eclogites, and then you have all the schists here, like this one, that is a pyrite, yeah. Here, what is this? That's a chloride schist. So, and these metamorphic rocks, most of them, the lower grade, orogenic metamorphic rocks, they are schists. So, and when they underwent metamorphism, let us say above 700 degrees Celsius or 750 degrees Celsius, then you are forming then a bipartite, so and then a granulite. So there is no longer any schistosity visible, yeah? So, and then you have the local, the contact metamorphic rocks, and that you should also know by now from ES106. You have just a magmatic intrusion somewhere. So, and then the surrounding rocks becoming then metamorph overprinted. These metamorphic rocks thus do not show longer any schistosity, yeah, because they were not metamorphosed under tectonic force. It was just heated up, yeah. So I mean, you can do this also in an experiment, yeah. I mean, you can use a car driving against the next wall, and then when this car becomes metamorphic overprinted, and you can see it is strongly folded, yeah. So, and whereas if you have a contact metamorph overprinted car, then it is burning, yeah. So that means the shape is still the same as before, or nearly the same, but it's just burnt, yeah. So, next slide. So then the sedimentary rocks, you know this by now as well, that is products of weathering, yeah. That means you have mechanical and chemical destruction or destroying of rocks. Then you have the transport, so and that is the mechanical movement of rock fragments. These are detritus and dissolved components by flowing water, and that is gravity driven. So, and that is just weathering took place. I mean, here in Fiji you have a lot of weathering, yeah, and that is why, because it's raining every day, yeah. So, and then these rocks becoming weathered. So, and then the transportation, that is just via a river, yeah. So, and these sediments becoming then deposited somewhere at the coast. So then you have the deposition that is of detritus in low energy environment, such as in deep sea basins, continental shelf platforms, lakes, braided river system, chemical precipitation of minerals from oversaturated solutions like calcite, gypsum, and pallite. So, and when you are just reading this, we have the chemical precipitation of minerals from oversaturated solution. That is just what we are doing here, yeah? So, but here we are not growing calcite, a gypsum or a halite. Here we are just making crystals, yeah? So, but anyway, I mean, you can also make a calcite crystal, and the calcite crystal, that is probably here. No. But here, for example, we have the halite, so yeah, you can leak on it, and then you can tell me what the taste is. You can really do this, that it's not poison, because salt is disinfecting. Yeah, just the number of the calcite.
$55.
55. That is actually a rhodochrosite, 55.
Ah, calcite.
Now you can look into this later. So, and calcite or calcitic rocks you have here on the witty level, also some of them around. Yeah, you have here these limestones. So then we have the process of diagenesis. That is the reduction of the pore space. Yeah, you have then by sedimentation, you have your sediment somewhere in a shallow water or in the deep sea floor. So, and then it becomes deposited, and when it becomes deposited, then the next step is the diagenesis, and there you are getting at first then the water out of the pores, yeah? Out of the pore space. So, and there we have then the transformation of carbonate into mud to limestone, yeah? So, and then, to clay. So, and that is actually then the beginning of very, very low-grade metamorphism, yeah? So then we have detrital sediments, we have gravels, conglomerates, breccias, we have sandstones, arkoses and greybuckies, we have shales, argillitics and siltstones, and we have volcanoclastic sediments. So such a volcanoclastic sediments, you can also see them here, and you will see them also during the feature. Does not matter if we are doing the feature here or in Polo, yeah, these these tubes you have here and in Polo. Yeah? So where else the shales, so in the argillites and the siltstones you can also find here, yeah? You can find here a lot of sedimentary rocks which have still shales inside, or actually these foraminifers, yeah? And the oldest ones of sedimentary rocks which you can find here on witty level, they are about 40 million years old, yeah? So, and if you have these forams inside, and the foram that is such a microfossil, and this microfossil, it was living, I mean now it's not longer living or alive, in a very shallow, warm water. So, and that shows us that 40 million years ago, witty level was still underwater, yeah, but it was close to the surface, yeah. So in the oldest rock from the oceanic crust, I have dated them on 47 million years. That was then actually the the beginning of the formation here of Witty level, yeah? So now the next slide, please. So now we have non-clastic sediments, we have limestones and dolomites, which you can find here. Then you have cherts, ironstones and phosphorites. You have salines and other evaporates and carbonatic sediments. Yeah? So these are then all your different sedimentary rocks. And now we are coming to this slide. This slide is actually explaining a lot. That is the rock cycle. That is something like we had at the beginning of this class. Yes, you have here the subduction of an oceanic lithosphere beneath the continent. Here we have a continental lithosphere. On the way down, metamorphism will take place, and there you are transforming your basalts at first into green schists, and then into epibolites, and then into eclogites, and then you will form at the other stage granulites. So then this melt will rise up. So and the reason why you are producing here melt, that is because of the release of water from your hydrated rocks, which becoming now dehydrated. That is something very important to know, yeah? Because that is or explains how this planet is running. So and there is the most important thing on this planet, that is actually water. Because without water, there would not be any plate tectonic, and if you don't have plate tectonic, then no life is possible. So now you have at first, you are forming somewhere here, yeah, but here the picture it comes to the end, but somewhere here, you are forming your inchless rocks. That is inchless rocks becoming hydrated on the way towards the continent. That is very important that you have at first to hydrate them, then you are sending them down, yeah? Then they are becoming dehydrated, and by the release of water, you are producing them here in the mantle wedge melt, yeah? In former time, people thought always the melt comes directly by melting from the slab. That is not true. You have the dehydration of the stuff. Then you are creating the melt in the mantle wedge, and this melt rises then up because it has a lower density. Yeah? So and then some of the stuff becoming then here thrown out. Then you have your inchless volcanic rocks. Yeah? Some of the other stuff becomes stuck here. Then you have your granitic rocks, plutonic rocks. So in the surrounding area becomes then heated up. And then you are making there your contact metamorphic rocks. So and then here at the top you can see there are some clouds hanging around, yeah? Then weathering will take place of your rocks here. The sediments will become transported into the ocean or into the river, yeah? There it becomes then sedimentated, and then the whole thing starts again, yeah? So then we are going to the next slide. So and then we have different minerals in sedimentary rocks. You have carbonatitic minerals, yeah, that is the calcite and the dolomite. So then you have sulfates, that is the just gypsum, for example, or anhydrite. So gypsum and anhydrite is actually nearly the same. That is just calcium sulfate, and that is calcium sulfate with H2O inside. So it is then, if you are adding water to anhydrite, then you will form gypsum out of your anhydrite, and that is then blowing very, very up, yeah? Because of the increase in volume, yeah? So then you have the halides, yeah? Halide, that is just sodium chloride, and then you have sylvite, that is potassium chloride. So we are using actually for cooking purposes halide, whereas a cow uses sylvite, yeah, the potassium chloride, you know, they are leaking on them, yeah? So, and then you have the carmelite, which nobody needs. So, and then here finally we have the phosphates, and that is the stuff what you are carrying here around, yeah? Apatite, yeah. So now we are going to the next slide. So then we have the carbonates, like soda and trona. We have the borates, like borax, and we have silicates, yeah? And that is just when we are talking about sedimentary rocks, then these are the clay minerals, and the clay minerals are typically sheet minerals. Low pressure, low temperature sheet minerals. There you have then the kaolinite and you have the chloride. And here we have the oxides, like the hematite, and the hematite that is Fe2O3. Next. Here we have again the rock cycle, we don't need it now. So now we are talking about a small introduction into metamorphic rocks. So as I told you in the last 2 hours, your rocks undergoing always changes in pressure and temperature, yeah? So, and for example, if you are subducting an oceanic crust, then I mean while the slab is going down, you are increasing the pressure and the temperature. So, and then some minerals, so I told you this also before, when you are increasing the pressure, then the density becomes higher because you are pressing your rock together, yeah? So it then means a lot of rocks like SiO2, that is quartz, changing then their crystallographic symmetry, yeah? And other rocks, they are changing always their mineral chemistry, yeah? Together with the with the symmetry, yeah? So, for example, I told you also before, when you are looking for a garnet which is undergone a high pressure phase, has then more calcium inside, and the calcium concentration is then an indicator for the pressure, whereas the magnesium or ex-magnesium, that is then the indicator for temperature. So we here have now the quartz, and quartz has always the same chemistry, yeah, you know this by now, that is SiO2. So, but it is the changing their crystallographic symmetry, And here at the Earth's surface we have a low quartz, and you know by now how the low quartz looks like. That is this guy, you have seen it now a couple of times, yeah? So, and if you are increasing the pressure, then you are forming here, at this pressure temperature condition and coincide, and here are at pressure conditions of more than 80 kilobars, depending on the temperature as well, you are forming then a stishovite, yeah? So, and you can calculate these transitions, yeah? So, and now the question is, I mean, now we are sending this piece of rock down, yeah? So, and after it can become very, very fast to the Earth's surface, yeah? That is the via volcanic eruption when it becomes just picked up in depth, yeah? Or by a kimberlite, yeah? Kimberlite are actually very fast. They are just shooting through the Earth's mantle with a speed of 300 meters per second. That is Mach 1, that is a jumbo jet, yeah? So, and these are just cracks, and they are blowing up and running then through the Earth's mantle and crust. So, or you can have them, find them later on the Earth's surface just by the process of weathering, yeah? Because you are always removing by weathering stuff from the surface, and from below it's growing, yeah? So because while your continental crust, for example, or the oceanic crust is cooling down, then it becomes always more and more thick, yeah? So, but now theoretically, this stishovite shouldn't go back when it comes to the Earth's surface in the low quartz modification, yeah? And that is indeed the fact, yeah? So, but now how can you prove that there wasn't stishovite? That is a very interesting thing. For example, you have here a garnet, yeah? And not, for example, one find them or can find them or indicate them in other minerals, and in such pressure and temperature conditions you have garnets as well. So, and when the quartz or the stishovite occurs as inclusion, for example, in a garnet, then they will survive, or at least partly, on the surface, yeah? Because then they are enclosed, and then they cannot go into their low quartz modification because there is no space. And if you are looking at such a garnet under the microscope, then you can see around the stishovite, you have then a lot of micro cracks. That is because your stishovite likes to go back to the low quartz modification. So now and that is when you are increasing the pressure. When you are increasing the temperature, then you are increasing the volume. And the best example for that is if you are looking for the water system, yeah? I mean, there one can see it best because at 100 degrees Celsius you are making a steam out of your water, out of your liquid phase. You are making a vapor phase. So, and I mean, you can just sit there on the cooking pot while the water is boiling. It becomes then a little bit hot, yeah. But then you can also feel the pressure because you have the deep increase in volume. And you have also a strong increase in the entropy. And the entropy, we will also talk very soon about it. The entropy is actually just the disorder of a phase. So when that is caused, when you are, I mean, what happens to your water? If you are looking for the system water, you have ice, you have liquid water, and you have steam. So and then, I mean, what happens to your atoms inside the ice? So they are very, very constant and they are not moving that much around. So whereas if you have liquid water, then your atoms veering much more around, yeah? So if you have steam, then they are just flying through the space, yeah? So and that is for every other mineral as well. One have also to be always very carefully what you are saying with the water, yeah? Because if you are using the old definitions from 100 years ago, which people are still using, then water is per definition not a mineral, yeah? Because it is in the present form, it is not crystalline, yeah? So, but whereas when you are looking for ice, ice is a mineral because ice forms crystal, yeah? So, but mineralogy or metrologically, we are treating water like a mineral because when you are doing your calculations, you are treating them all as phases. So in the term phase, that comes actually from the chemistry. That comes from the chemistry, and they are treating them all as one thing, which is actually the best thing to do. So you have then always with changes in pressure and temperature, you have always changes in the volume, yeah? In the volume and in the density, and also now in the entropy. So next slide. So then we are looking now for minerals, yeah? So and now we are using a very simple system. We are using always in petrology systems to classify a rock. So and in this system we can then do some mineral chemical calculation. So here we have, for example, the MSH subsystem. So we are using always the first letter of an element. So M stands then for magnesium, S stands for silica, H stands for water. So these are olivine normative rocks. And if we are talking about olivine normative rocks, then we are looking for Harzburgite. And if we are looking for perinotites, and if we are just looking for magnesium, silica, and water, we are looking just for Harzburgites, yeah? And you know from our last class, last week, what are the minerals in such a Harzburgite can be? I mean, At high temperatures, you have then the Endstatite and the Forsterite. So in the Endstatite, you know by now, I gave you the formulas. That is MgSiO4. So and then the Endstatite, that is a magnesium-bearing orthopyroxene with Mg2Si2O6. So then you have the anthophyllite, and the anthophyllite that is now an amphibole, yeah? The amphiboles you don't know by now. So then I will show them you now. Yes. So the amphiboles, that is now just the jump in, yeah, but you need them now. And you are putting this just in your booklet together with all the other minerals. So you know from last week the anthophyllite, that is an amphibole, and amphiboles are very, very complex, and they are double-chain silicates. So when such an amphibole has here also an such a gap inside, yeah, we are calling them the A space. Then you have 2 and 4 spaces. These are the octaeder spaces. So then you have an M3 space. There you have also, I think so, 1 or 2. You have actually 3 and 3. So, and then you have an M2 and an M1. So, and that should be 7. 1, 2, 3, 4, 5, 6, 7. So then you have your, and the M1 is the smallest space, and the M4 is the biggest space. But that you should know by now as well. Then you have the tetraeder spaces. So in tetraeder spaces you have 8. So and then all the amphiboles, they have 22 oxygen and also an OH2 group. So and now we are coming just to this guy. That is the anthophyllite here. That is an orthoamphibole. Then here it is empty. And then we have Mg, 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 Mg. So you have then 7 magnesium, yeah? Yes. Then here you have Si8, O22, OH2. Finishes the anthophyllite, yeah? So then you have the coming tonight, and the list with all the mineral names and with all the formulas, it's also uploaded on Moodle. Did you find it? Then check it. So then we have the next one from the orthoamphiboles, that is the coming tonight. So the coming tonight is actually very funny, yeah? Because, for example, if you are asking your boyfriend, are you coming tonight? And he thinks you are talking about him while you are just studying these things here. That is then just a mixture between magnesium and iron. So the coming to light is then formed at lower temperatures. So, and then we have beneath, we have the runnerite. So they have here all the space. So in the runnerite has then more iron inside. So then you have here just 7 iron. So, and these are the autoamphiboles. So, and when we have autoamphiboles, we have also kleinoamphiboles. And therefore, we have the tremolite. And the tremolite has the shortcut trem. So then you have here also space. So but here you have then a calcium, and the calcium is sitting always on the bigger octaeder spaces because the calcium atom is bigger. And then you have Mg, 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 Si8, O22, OH2. So then you have the next guy, and that is the actinolite. So you have the calcium, calcium, magnesium, magnesium, iron, 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 for example, something like this. Yep, Si8, O22, OH2. So then what will we have next? We have the hornblende. So now we are putting here on this space the sodium. So because the sodium atom is bigger than the calcium, calcium, calcium. So now we have here the sodium, and then we are putting here magnesium, magnesium, iron, iron. Then we have to balance this sodium here. So, and then we are making here an exchange. We have here aluminium And then we are kicking one silica out. Si7, O22, OH2. So and now I will give you also the glaucophan. So because the shortcut is GLN, glaucophan, and the glaucophan is actually making the blue schist blue, and that is because of the sodium inside. So then you are putting here on these places in front the sodium, but you have still the gap, yeah, you have still the gap here. Sorry for doing such a mistake. Sodium, then you have here also always magnesium and iron, yeah. I have just to watch it now. Then we are making here Mg, an iron, Al, There we are putting 8 silica. Silica, O22, OH2. So that is now some of the amphiboles. I mean, the whole amphibole group contains a lot of end members, yeah? So, but you must not now study all the end members from the amphiboles. But at least that you have the antophyllite, yeah? So in the antophyllite, I mean when we are just going to this place here, where you have the chrysotyl, the antigorite, and there is another one that is the lizardite. They are also polymorph minerals, and polymorph minerals, you know this by now as well. These are minerals which have always the same mineral chemical composition, but a different symmetry, yeah? These are polymorph minerals. So and now you have at very low temperatures, you have the chrysotile, yeah? So in such an antigorite, they have the formula, it is Mg3Si O5OH4, yeah? So these are strongly hydrated minerals, and the brucite as well. The brucite is just the MgOH2. These are all strongly hydrated minerals. So, and now we are coming to this very important point. I mean, at the middle ocean ridges, you are forming them, yeah? For example, you can also form them in other settings, but for example, you are forming this guy at the middle ocean ridge, yeah? So, and this guy was actually formed at temperatures above 1200 to 1400 degrees Celsius, when it's even more, yeah? So, and now you are sending them from the middle ocean ridge towards to a continent, yeah? So in there, the oceanic crust becomes partly hydrated. Not everywhere, only partly. So because there is of the water above, yeah? So and where is this? Where does this hydration take place? That there are everywhere these huge faults. So I mean, if you are looking or if you are just using Google Earth, then you can see, I mean, when you are removing the water, or it's actually always removed in Google Earth, then you can see perpendicular from the mid-ocean ridges, you have always these huge faults. Yeah? Have you seen them? So in there you have a lot of sedimentation, and there you have a lot of hydration. Yeah? So you are subducting them, or you are hydrating them, the oceanic crust, partly. Yeah? Partly. So and what happens then to your oceanic crust and to your mantle slab below? I mean, these faults can go down into the oceanic crust. They can be up to 75 kilometers deep. Yeah. So, and there you have this hydration. So, and now what happens when you are hydrating this material? I mean, you have originally this material, and now you are making a serpentine out of it. What happens to this material? So, I mean, if you are hydrating it, what happens then to the density? So, when you are just, for example, you will be here for the next 20,000 years, putting there always water on it, yeah? Then you are hydrating this. So there is an alteration, yeah? So, but what happens when you are making from this olivine and serpentine? What happens with the volume and the density? Will it blow up or will it shrink? No, it will blow up. The volume will blow up, so the crystal, the new formed crystal which you are forming out of this will become bigger, yeah? So the volume will increase and the density that will decrease. So, but what happens then to the weight of your whole subducting slab? The weight from the whole subducting slab, because the material becoming lower dense, will be less. Yeah, that will be less. So, and then you have an ophiolite. Did you hear any time before what ophiolites are? That is something very, very important, even more important than the coming tonight. So, now we need then two pictures. Here we have, for example, the continental crust, yeah, CC. So, and then you have here a normal subduction, yeah, like it is that is OC. And And here, that is the upper part, and the lower part, that is the mantle slab. And then you have here some water, and here you have a ship. So again, you have a normal subduction. So, but what happens now? You have again a continental crust. What happens now when your slab becomes strongly hydrated on the way towards to the continent? Then the density will decrease, the volume will increase, then you have not a subduction like here, no, then you have an obduction. So then you are putting your oceanic crust together with your mantle slab on the continental side, yeah? So and these complexes are then called ovulites. So in the next ovulite here, that is actually a big ovulite complex that is in New Caledonia. So therefore, your slab will become then hydrated. So and if it is not that much hydrated, then it will become subducted, yeah? So then you have here cracks going down up to 75 kilometers, yeah? So, and their hydration will take place, and then while it goes down, then you are increasing the pressure and the temperature, yeah? So, and then your hydrous minerals will break down, yeah? They will just dehydrate, yeah? So, and then you are forming, at first you have the brucite, the antigorite, and the chrysotile. Your chrysotile goes then very early at about a little bit more than 200 degrees Celsius, depending on the, or let us say 250, yeah? Depending on the pressure, it goes then into the modification antigorite and brucite, yeah, there you have the first mineral reaction. Then your brucite will break down here, and then you are forming your forsterite, yeah. Then you have the mineral paragenis, antigorite and forsterite. Then later on, the antigorite will break down, and you are forming from your antigorite and talc. And the mineral chemical formula for talc you have already, and compared to the antigorite, talc has only one OH2 group, yeah? So that has the less water inside, and the system is now on the way down, releasing more and more water, yeah? Which leads then here into the formation of melt. So, and finally, then you are forming later the antophyllite here out of the talc, and finally you have again a totally dehydrated rock containing then forsterite and andesite, yeah? So your rocks are undergoing always changes in their mineralogy, and that is caused by changes in pressure and temperature, yeah? I mean, there are also some other parameters, yeah? It's the fluid inside, yeah? The composition of the fluid. I mean, when your rock is totally dry, when there is no water available, then nothing will happen. Yeah, I mean, you can do this at home in your kitchen. You can make spaghetti noodles in a pot with water, and then you are running the second experiment. You are just throwing the spaghetti noodles inside without water, then you are heating both up, and the result is totally different from each other. So that is now the presence of fluids, and we will also discuss this later on more in detail. So, but now we are running there always, because of pressure and temperature changes, our mineralogy of the rocks will always change, yeah? That will always change. This one you have now to put a little bit more on the top, because it's already lying on the ground. That is group number 4. So, next slide. So, and there we have now different processes. We have a regional metamorphism, yeah? So that means we have that is metamorphic events related to a subduction process. There we are dealing with high pressures but lower temperatures. Then we have continental collision processes. There we are dealing with moderate pressures and moderate temperatures. So, and if you are looking at these rocks, then the products of these rocks are strongly deformed with typical deformation fabrics. Yeah, that is then the schistosity. And here you have some very, I mean, in the one which I showed you this morning with the green schist, you can see very, very nicely and very, very well the schistosity. Can you see it? You have to look from that side. Yes. So can you observe schistosity? So if you are looking from that side, especially from that side, you can observe very easily the schistosity. Yeah? So and that is typical for the formation of this type of rocks. So now we found this rock just by accident a while ago here in the middle of Movie3 ES203. So now I have to think about how can this rock become formed here. So I mean we do not have a subduction zone here, we have here I mean 2 subduction zones. The other one is in Tonga and the other one is in Vanuatu. So then we must have a collision going on, yeah? So and that is a very interesting thing here, because if you are, you can just use again Google Earth, yeah? And you are watching Movie3 ES203 from above, then you can see all the different volcanoes, yeah? There are a lot of them. So when you are dating all these different volcanoes, then you what can you observe? They have all a different age, yeah? I mean, the oldest rocks here in Movie3 ES203 are 47 million years, and the youngest are just recently. So, and I mean, if you are looking for the whole South Pacific, I don't know, is somebody here from Tonga? Yes? Then you have heard about Huia Tonga, yeah? Huia Tonga. That is just a volcanic island which popped out of the water 3 years ago, yeah? So, and then you have in former times, I don't know when, a couple of million years ago, I mean, I have still to date this rock. You have everywhere this all these volcanic parts popping out of the ocean. Yeah? So at a certain time, they just become moved together. So and then this is just a metamorphosed basalt. Yeah? And if you are looking for a basalt, you can just check it here. The basalt looks completely different. Yeah? So, but you have the mineral chloride inside, and there is a sheet silicate that shows also that this basalt was before strongly hydrated. Yeah? So, and this is actually just very important to understand the Earth's history. Yeah? So, and the whole planet is always running in these cycles. I did a lot of work in Tanzania, actually most of my work. So in Tanzania, the same thing happened just 640 million years ago. Yeah? We had everywhere these small shields, and 640 million years ago, they were all moved together. So in the original, the protolites there, they are ranging in age between 2,900 million years and 1,100 million years. Some of them are formed at 730 million years. So in that 640, they were just moved all together to produce granulite-facious rocks. Yeah, you will see this next week when we are talking about granulites. These are high-grade metamorphic rocks. Yeah. So and now, I don't know, are you aware of the geotectonic setting here? Can we just check the slab figure? There should be my slab figure somewhere.
What in this slab?
No, that is a single picture that is. Just check it in 301 or 303. So that's this one. This one. So that is a figure which I made with my Illustrator programs just a while ago, yeah. So and that is something about the geotectonic setting here, yeah. So and then you can see here you can see the Fiji microplate. That is Viti level, that's Vanua level, this is, I don't know, over now, yeah. Is it? Taveuni, and that is Koro Island. So then you have here Vanuatu, and here you have some Tongan Islands. So again, the one plate here is dipping down here and producing this the Tongan rocks, yeah, that is dipping down from east to the west. So then you have here the next subduction zone, dipping down from west to the east, and there you have Tonga. So and I mean now in Tonga you have always volcanic eruption. Yeah, that is that the volcanic rocks in Tonga are chemically totally different from those ones here, because they are subduction related. Yeah. So and therefore, in Tonga and in Vanuatu, I mean in Vanuatu, you have the volcanic eruptions. Yeah, in Tonga you had it just recently, because it pops just out of the water. And there you have also the chances to have an earthquake there is much higher than here, yeah, because it is because of the active subduction. Yeah. Here the earthquakes, I mean here you have everyday earthquakes, but you cannot feel it because the epicenter is in a depth ranging between 400 and 600 kilometers, and so it will not affect us, yeah? So, and now we have to see, and these guys, I have this one, the screeches, we have here just found here somewhere in the middle, yeah? So, and that means we have here a ridge system and we have here a ridge system, and then this plate is moving there and the other one is there, and then you are forming here the metamorphic rocks, yeah? That is then collision related, yeah? In a small scale, yeah? So, and that is because that is all what you can read out of rocks, and therefore they are important. So now we are going back to our slide, to our show. So and then you have here this metamorphic rocks, just the page before. The page before, no. The afterwards, this one, yeah. So and then you have the examples, these are the Scottish Highland, the Central Alps, yeah. We have here a lot of rocks lying around from the Alps, Coast Range in California, then the Scandinavian Caledonians and New England. So and these are all from active orogenic belts on this planet. So and here the next high-grade metamorphic rocks here you have in New Caledonia. In New Caledonia you have these ophiolites, as I just mentioned you a couple of minutes before. Then you have eclodites and you have blue schists. So and now we have here the screeches. So and if you are waiting, let us say, for another 5 million years, then you are making from the screeches making an amphibolite, yeah? Because the movement is still going on. So the next slide now. So then we have local scale metamorphism. And that is, as I told you before, that is related to magmatic intrusions, yeah? And then you are forming contact aureoles. And this is then a contact metamorphic zone, and therefore you are forming there other products. These rocks are then called so-called hornfelds. Hornfelds are formed at low pressures but high temperatures, because they are always related to a hot melt, yeah, then you have automatically a high temperatures. So, and rocks, they are typically undeformed, yeah, and they are fine-grained, and we are calling these rocks hornfelds. So, and there you have some examples. That is in the Alps, Bargel and Adamello, that is in Switzerland and in Italy. So then you have the Oslo Rift, Scotland, Sierra Nevada, the Idaho Batolite, and the Rogaland Aureole. So then next slide. Yes. So and there we are stopping now, yeah? So then just watch your crystals, yeah? So and Satan will upload sometimes this week the videos, yeah? You have now 2 from this year, but the other ones from last year are still all there. And I will then also upload the test number 1. So I will upload test number 1. You are writing 2 tests. So in this, but I make this test always as a homework, yeah, because I mean you should study, yeah, and you should then hand in this test before the midterm semester break. That is now 4 weeks there, yeah. So, and then we are doing the same with test number 2, and the examination is the combination of these two tests.